Hello, my name is Kurt Hondl, and I'm the Deputy Director of the National Severe Storms Laboratory. Prior to becoming the Deputy Director, I was the Phased Array Radar R&D Program Manager, and I still perform that function. Observations are very important to meteorologists. Radar is the primary tool that meteorologists use when issuing warnings for severe weather, particularly tornadoes, severe thunderstorms, flash floods. As Jack had mentioned, NSSL has been involved in radar research since the very beginning. In fact, in the 1970s, they developed the Doppler weather radar capability and observed the first tornadic vortex signature in Doppler weather radar. And that eventually led to the deployment of the WSR 88D network, otherwise known as NETRAD. NSSL was also a pioneer in the development of dual polarization technology, which led to an upgrade to the NETRAD system in 2012-2013 timeframe. Throughout this whole period, NSSL has been working to improve the weather radar capabilities for NOAA. And beginning in the early 2000s, we started looking at phased array radar as a potential replacement for the NETRAD system. The current NETRAD network is estimated to be viable through 2035 or perhaps longer. So in the early 2000s, the Navy agreed to loan a SPY-1A antenna system to the laboratory. Its primary mission for the Navy was as an aircraft and missile detection radar. The one they gave us was serial number 1. It was a battle spare that they no longer needed, so they loaned it to us, and it was modified to perform as a weather radar. It became operational, was turned over to us officially in 2003, and then in 2004 we observed our first tornado with the phased array radar. Through the first several years, we're using the radar to look at different meteorological events, severe weather, tornadoes, hail, those types of things. And then we began to use it to understand how forecasters could use the rapid update data that the phased array radar provided. As I mentioned before, NSSL had also developed dual polarization radar, but the SPY-1 system was a single polarization radar. And we knew early on that we would have to integrate dual polarization and phased array radar if we were going to make the radar of the future. So beginning in 2007, we started our first development effort with our partner, the Federal Aviation Administration, and funded the development of a dual polarization panel, a very small version of a radar. And we learned from that, tested it, built something a little bit bigger. And ultimately in 2015, we had what we called the 10-panel demonstrator. Very descriptively had 10 panels together functioning as a radar. It was the first dual polarization phased array radar. And although the beam width was too large for detailed meteorological measurements, we were able to learn a lot from it with regards to operating the dual pole phased array radar, beginning to look at calibration issues and so on. In 2016, we dismantled the SPY-1A system to make way for our new advanced technology demonstrator, which I'll talk about in a little bit. So let me back up for a minute and talk about why NSSL is doing this research. Other than being NOAA's radar laboratory, it's something that Congress expects us to do. In the recent Weather Research and Forecasting Innovation Act of 2017, it explicitly called out the investigation of dual polarization phased array radar. And our Department of Commerce and NOAA plans also have objectives to reduce severe weather impacts. And our OAR strategy to make forecasts better, I'll modify that a little bit to make forecasts and warnings better, is laid out in that strategy as well, and also aligns with the National Weather Service's Weather Ready Nation initiatives to improve warnings and forecasts for severe weather so that we can save lives. Our grand challenge at NSSL is to ensure that NOAA has the best radar tools to accomplish its mission. So we have to evaluate and understand the advanced technologies of dual polarization radar, and then apply them for usage as a weather radar. And we have to examine the costs and benefits of phased array technology so that we can be in a position to have the knowledge to make a decision when it comes time to replace the current NETRAD network. And radars are a crucial piece of our national infrastructure. So you might be asking, what's so great about phased array radar? Well, the number one thing is its flexibility. It can steer its beams electronically rather than being tied to the mechanical rotation of a dish radar like the NETRAD system. So on the right-hand side of this animation, and you'll probably want to click on the link in the PDF to see this full animation, because I'm sure the video doesn't quite do it justice. But on the right-hand side on the top is the reflectivity, and the bottom radial velocity from the NETRAD radar, updating approximately every 5 minutes. On the left-hand side, we have the radar data from the phased array radar, the SPY-1A system, which was updating every 1 minute. And this allows the forecasters to better track the signatures and see the evolution of those signatures to provide better warnings. So along with the meteorological research of this system, we also use the SPY-1A system to look at new technologies that phased array radar offered. We also examined how it might be used as a dual purpose radar and other techniques to improve the data quality of a phased array radar system. So we used the SPY-1A system, as I said, for a little over 10 years. And what did we learn with that system? Well, we demonstrated that we could better understand the storm evolution processes. We demonstrated that with forecasters that you could, that there was potential to increase tornado and severe weather warning lead times. And we also demonstrated that we could take this rapid update data and put it into our warn on forecast models to provide better future guidance as well, to further extend lead times for severe weather. So since the last review, not only have we developed our new advanced technology demonstrator, but we also wrote several publications regarding phased array radar, 44 of them to be exact since the last lab review. And we also wrote 9 technical reports. The technical reports are an important piece of our collaboration with both our research partners and external collaborators and radar industry in general. It's information that probably isn't appropriate for a scientific journal, but is necessary so that we can communicate our requirements, what we've learned, with other people in the industry. And literally everything that we've been doing with these radars is being done for the first time. And so when you have a radar and you want to ask yourself, how are we going to calibrate this? You have to start from scratch and figure out how you're going to do the calibration, how you're going to do the evaluation, what issues you're going to run into, and then you learn from that and you make that process better. So we are pushing the boundaries. Based on the experience we had with the SPY 1A system and our small scale engineering demonstrators, we decided to build the Advanced Technology Demonstrator. It's the first dual polarization phased array radar built to be a weather radar and to be able to be used for meteorological research as well as engineering research. And Congress checks in on us every once in a while and asks us to provide reports of how everything is going. And so we've developed or have written several reports to Congress and provided numerous briefings to both Congress persons and their staff to better understand the progress of the program. And I would have to say that you know, one demonstration of our performance is that Congress has continued to support the program with increased appropriations over the years. So we didn't build the Advanced Technology Demonstrator by ourselves. We had a whole crew of collaborating organizations. The logo of logos on the left shows some of the prime research collaborators under the development of the Advanced Technology Demonstrator. It takes a small army to build something like a phased array radar and another small army to maintain it and calibrate it and keep it in shape for research purposes. We also had other industry partners that we were involved with various aspects of our research over the last several years that are also indicated on this slide. So we have a couple of presentations coming up, and I'll give you a brief overview of what they are. And so, you know, one of our main objectives in building the Advanced Technology Demonstrator was making sure that we could calibrate the polarization characteristics of a phased array radar. And our next talk will talk about some of the unique things we had to do to be able to do that. And then the next talk will talk a little bit about the radar data quality and the trade-offs that we have to pass back and forth between coverage, speed, and accuracy of the radar data. And then we also have to evaluate the risks versus the benefits of the various trade-offs that we've made. And then last, you'll see some of the benefits of the rapid update dual polarization data. And all of this research is designed to establish NOAA's knowledge of dual polarization phased array radar technology so that we can be in a good position when it comes time to make a decision about the future replacement of the current NETRAD program. I'll now turn this over to Danny to provide a little bit more of an overview of the Advanced Technology Demonstrator.
Hello, my name is Danny Wasielewski. I'm an electronics engineer with the Radar Division of the National Severe Storms Laboratory, and also the team lead of the Radar Engineering and Development Team. Before we get into some of the more scientific and observational aspects in the following presentations, I want to use my time to talk about the Advanced Technology Demonstrator system itself. My hope is to give you a virtual tour of sorts to help you appreciate the scope and provide a visual context for the talks that follow. First, what is the ATD? Kurt has already given us a preview, but to recap, it is NSSL's newest research radar, the first full-scale S-band dual polarization phased array radar built from the ground up with the weather mission in mind. On the left, you see the radar facility originally built for the SPY-1 radar, which has now been repurposed to house the ATD since 2018. The reason the ATD was built was to explore the combination of dual polarization and phased array technology. Dual polarization is a technique pioneered at NSSL in the 90s and now operational across the National Weather Service. It gives forecasters more information about what is being observed. For example, to discriminate between regions of rain, sleet, and snow in a winter storm. Phased array radar, as Kurt explained, allows more flexible scanning without the need for moving parts. This enables faster scans and the ability to adapt the scan strategy to the weather being observed in real time. There are two main purposes of the ATD. First, it will be a major research tool for NSSL's meteorological researchers. Dual polarization phased array will give our researchers new insight into the evolution of storms by providing more information at a higher temporal resolution than ever seen before. Second, but just as importantly, the ATD is a fact-finding mission for the National Weather Service. We hope that by the time the WSR-80AD needs to be replaced, that this work will make a compelling case for the benefits of phased array radar and also provide answers to some of the real pressing challenges toward adopting this technology. Here's an inside look at the ATD radar itself. On the left is the front side of the radar antenna. You will immediately notice it looks nothing like traditional parabolic dish radars. Instead, we have a flat face composed of 76 tiles or panels. Each panel has 64 individual small antennas that all must work in concert, 4,864 in all. The panel-based architecture makes the system maintainable. It also makes it scalable for different sizes of antennas. As it stands, the ATD antenna is somewhat smaller than the WSR-80AD. However, it is still quite imposing at 14 by 14 feet. You can see in the middle picture, a person on a stepladder is completely dwarfed by the radar. You can also see how complex it is. There are more than 2,000 connections and a mile of cable to connect the antenna in what we call the radar backend. One of the clever engineering decisions to make this feasible was to put nearly all of the radar equipment on the pedestal. This antenna can move in elevation from where it sits to pointing straight up, even all the way over to 180 degrees. Keeping the RF and the power equipment in these white racks on the sides of the pedestal allows them to serve as counterweight for the antenna, and it also minimizes the number of connections going through a moving interface. The blue rack in the background houses 16 high-power multi-core servers that process enormous amounts of radar data in real time. As with the radar hardware, it took a monumental effort from software engineers from 3 organizations to make the system a reality. We knew from the outset that one of the most significant challenges for dual polarization phased array would be achieving a tight and consistent calibration. Dr. Sebastian Torres will give more details on calibration in the following talk. For now, I will only highlight that one of our strategies to address this risk was to build in as many calibration tools as we could to take measurements. There are techniques to use the sun or light rain for dual pole calibration, so we designed the system to be able to point anywhere by moving in both azimuth and elevation. There's also a small test antenna inside the radome for taking measurements. But by far the most important tool we have is the calibration tower. The radar engineering team did the legwork to have a 150-foot tower erected about a quarter-mile north of the ATD. Underground fiber optic lines provide communication and RF to the calibration tower, so it can be operated in sync with the ATD. The tower can receive, it can transmit, it can even delay and rebroadcast a pulse to simulate a target far away. The takeaway here is that significant engineering work went into not only the ATD, but even the infrastructure around it. As you can imagine, this was a major undertaking, which took several years and, in Kurt's words, a small army. Kurt already showed that NSSL was investing in the early development of dual polarization phased array panels in the early 2010s. By 2015, we had a completed prototype radar built in cooperation with MIT Lincoln Laboratories and OU. As that was nearing completion, in 2014 we received the green light to pursue the full-scale ATD radar. Design and production took about 4 years of work from NSSL, SIMS, Lincoln Laboratory, and General Dynamics before the pieces were finally brought together and installed in Norman in 2018. Thereafter, it was still another 3 years of integration and rigorous testing to prove that the system was calibrated and that the weather products could be trusted. And that brings me to the current engineering status before I hand off to the next speaker. The culmination of our system test effort is an important milestone called Initial Operating Capability, or IOC, which was declared on April 30th of this year. IOC means that the radar is deemed qualified for meteorological use. And as it happened, we had a major hailstorm in Norman just hours after the final system tests for IOC were completed. The storm came crashing through the radar site, destroying the roof and the windows of the adjacent office building, but not before we captured the striking radar imagery on the right. Fortunately, the ATD itself did not suffer damage. Though IOC means that the weather mission can start, IOC does not mean that the engineering effort is complete. Our near-term work focuses on more robust, reliable operation and improving the repeatability of calibration measurements. Beyond that, we need to start playing that second crucial role as fact-finders and inform the broader knowledge community of the design considerations and lessons learned to make future dual polarization phased array radars even more successful. And with that, I will conclude and invite Dr. Torres to share about some of the challenges and capabilities.
Hello, my name is Sebastian Torres. I'm the Serial Assistant Director for Radar Research and Development and a Senior Research Scientist affiliated with the Radar Division at NSSL. I also lead the Advanced Radar Techniques team, where one of our main research thrusts is the exploration of phased array radar technology for weather observations. In this presentation, I will describe some of the biggest engineering challenges and opportunities associated with the use of PAR technology for weather observations. And I will give you a summary of some of the work that we're doing to overcome the challenges and take advantage of the unique opportunities afforded by phased array radars. Since the initial deployment, operational weather radars in the US have experienced important technological revolutions. In the 1990s, the NexRad network introduced Doppler radar technology and the capability to measure winds. In the 2010s, the radars were upgraded with dual polarization radar technology, which provides additional information, for example, about the type and intensity of precipitation. PAR technology could be the next technological revolution. With this technology, the radar beam can be steered electronically, giving users the ability to control how, when, and where the radar scans. However, there are important engineering challenges that must be addressed before this technology can be adopted operationally. Our goal is to completely understand and reduce the risk associated with the use of this technology. Ultimately, our work will inform important decisions about future operational weather radars in the US. So let's start with the first big challenge, calibration. Weather radars use measurements of echoes from the atmosphere to derive meteorologically meaningful parameters. Calibration is the process by which these radar measurements, for example, the strength of echoes, are accurately related to physical properties of the atmosphere, for example, the intensity of precipitation. In other words, calibration tries to account for the influence of the radar system itself on the radar measurements. The shape of the radar beam is one of the main radar characteristics that needs to be accounted for in weather radar measurements. On polarimetric radars, the horizontal and vertical polarization beams must be precisely characterized so that the resulting observations convey accurate meteorological information. With phased array antennas, there are two aspects that make calibration a big challenge. One is that beams are formed by combining signals from thousands of smaller antennas. This is what allows the PAR beam to be electronically steered. The process, referred to as beam forming, requires precise synchronization of signals and accounting for system imperfections. On top of that, when the PAR beam is electronically steered, it changes in more than its pointing direction. As a result of electronic steering, the shape of the beam changes. For example, it gets broader as the beam is steered away from the perpendicular to the antenna, and the orientation of the dual polarization fields changes. For example, the horizontal polarization is not parallel to the surface of the Earth, and the vertical polarization is not orthogonal to it. These radar effects must be precisely characterized so that they can be accounted for in the production of radar data. As challenging as the calibration process is for just one beam, as in the case of a dish antenna, it is orders of magnitude more challenging for a PAR antenna because each electronically scanned beam must be individually calibrated. Here is a preliminary demonstration of PAR calibration using the Advanced Technology Demonstrator. The top row in this image shows fields of uncalibrated radar data. These are raw data that were obtained without taking into account the influence of the radar system on the radar measurements. As expected, we can observe the impact of not properly accounting for the beam changes that occur when the beam is electronically steered. For example, we can see artificially elevated values of differential reflectivity and differential phase towards the edges of the scanning sector, where the beam was electronically steered farther away from the direction perpendicular to the antenna plane. The middle row shows calibrated ATD data. where we can see that the beam steering biases have been significantly reduced. Additionally, the ATT calibrated data compare fairly well with data from a nearby next-red radar, suggesting that the calibration process worked well. Another important engineering challenge associated with the use of PAR technology for weather observations is choosing an appropriate system design. One key system design decision involves the selection of the antenna geometry. For example, should we use a force-phase planar array, a cylindrical array, or a rotating single-phase array? Each of these geometries provides different capabilities and requires different scanning philosophies. Another key system design decision involves the selection of the antenna architecture. For example, should we provide access only to the combined signals from all antenna elements, to the combined signals from several groups of antenna elements, referred to as a subarray, or to the individual signals from each antenna element? This is referred to as an all-digital array. Answering these questions is not trivial because it requires considering important trade-offs between cost and capabilities. That is, while more complex systems have more advanced capabilities, they also have a higher price tag. In general, finding a sweet spot between cost and capabilities involves an iterative process. Specifically, starting from a set of functional requirements, we can propose a concept of operations that meets those requirements. Then, a system can be designed with the capabilities and performance derived from the proposed concept of operations. Once the system is designed, we can estimate its cost and answer perhaps one of the most important questions: can we afford this radar? If the answer is no, we have to make changes to the requirements, the concept of operations, the system design, or a combination of these. Different concepts of operations and system designs could be tested by building different radar systems. However, a more practical and cheaper way to evaluate the impacts of changing requirements, concept of operations, or system designs is through the use of simulations. For this purpose, we developed a high-fidelity simulator that takes any weather case from the NextRad archives and produces radar data as if they were obtained by radars with different characteristics. This allows us to see how the radar data would look if we used radars with different designs without having to build these radars. For example, the simulator can be used to systematically study the impact of relaxing radar requirements. Here, we're most interested in requirements that have the largest influence on system cost. We refer to these as cost-driving requirements. An example of a cost-driving requirement is the need to provide sufficient spatial resolution to detect fine-scale features, such as tornadic circulations. Spatial resolution is directly related to the size of the antenna and thus has significant impact on system cost. For example, the radar beams shown here could correspond to increasingly cheaper radar systems that would produce radar data with increasingly degraded spatial resolution. As engineers, we can characterize these beams and quantify the impact to the data, but how would forecasters be impacted by this potential data quality degradation? To answer this question, we used our simulator to produce radar data for the same weather event as if it were observed by radars with beam shapes that are increasingly more degraded. These radar images were deemed as acceptable, marginal, and unacceptable by an experienced forecaster. When generalized to a wide variety of weather cases, results like these can be very useful to inform important system design decisions. So far, we have discussed two major engineering challenges associated with the use of PAR technology for weather observations: calibration and system design. Obviously, we would not be doing this work if the technology didn't bring significant opportunities to improve NWS warnings and forecasts. One such opportunity is the use of adaptive scanning. Adaptive scanning consists of changing what the radar does, for example, how it scans, in response to changes in the atmosphere. So instead of designing a radar that meets all functional requirements everywhere and all the time, we can design a radar that can selectively use its resources in smarter ways. For example, users don't really need the finest spatial resolution when observing stratiform storms, since these storms typically don't have any important small-scale features. PAR technology can give users the radar they need when and where they need it. Due to PAR's beam agility, scans can be seamlessly focused on regions of interest and tailored to get the best observations. Obviously, FARs cannot break the laws of physics. Instead, what they provide is a great deal of flexibility to achieve different radar scanning trade-offs. Simulations provide a practical means to develop, demonstrate, and evaluate advanced scanning techniques. In a way, adaptive scanning simulations give us the superpower to rewind time. The adaptive scanning simulator takes any weather event from the NEXRAD archives and produces realistic fields of radar data as if they were obtained with different scanning techniques. So the simulator can be used to compare the performance of different adaptive scanning techniques on the same weather event, or to evaluate the performance of a given technique on several events, or to evaluate the performance of a given technique on a given event using different radar designs. In other words, the simulated radar data allows the development and evaluation of feasible concepts of operations to meet evolutionary NWS observing needs. In this example, the same weather event is sampled using conventional and adaptive scanning. With the goal of producing rapid update data while minimizing interpretation impacts, the adaptive scanning technique uses focused observations by which regions without significant echoes are not scanned, and tailored observations where the radar uses different beam shapes and acquisition parameters depending on the spatial characteristics of the radar returns. For this case, the use of this particular adaptive scanning technique results in update rates that are on average about 5 times higher than with conventional scanning. We have made significant progress with PAR radar technology in the past couple of decades, but our work is not done yet. With the ATD reaching its initial operating capability only a few months ago, we are just beginning to demonstrate the polarimetric calibration. In the future, we also want to use this system together with our simulators to evaluate and demonstrate advanced capabilities provided by PAR radar technology. Additionally, we want to complete the analysis of antenna geometries and architectures. First, by focusing on the single-phase rotating geometry, and second, by demonstrating the capabilities of a null digital array. Finally, we will continue to assess the radar requirements and gain experience with the operation and maintenance of the ATD. Ultimately, everything we learn from our research and from the development and use of demonstrator systems will inform important decisions about the future operation of weather radars in the US. This is the end of my presentation. Thank you for your time and attention. Next, you will hear from Charles Kuster, who will be presenting an overview of phased array radar meteorological research and development activities.
My name is Charles Kuster, and I'm a research associate at CERO within the radar division, and we'll be speaking about how we have been using and learning from rapid update radar data in terms of observing severe and hazardous weather. One of the first steps we took when beginning to look at phased array radar data was to determine whether or not phased array radars would be beneficial to National Weather Service forecasters. If the WSR-88D network is to be replaced by a network of phased array radars, we first had to know that there would be benefits in doing so. This determination began with a series of experiments that spanned several years that sought to answer the question about whether or not radar update time mattered when issuing severe weather warnings. Those experiments were done using single polarization radar data, so our work now continues from there by looking at rapid update dual polarization studies. After several experiments known as the Phased Array Radar Innovative Sensing Experiment, or PARIS for short, we designed and ran the largest of these experiments in 2015. This experiment really was the culmination of all the other experiments and drew on what we had learned in the past to get the best possible data. For this PARIS, we brought 30 National Weather Service forecasters to the hazardous weather testbed over a period of 5 weeks. Each group of forecasters was here for a week, and during that time, they worked historical severe weather cases in simulated real time. Each forecaster worked 9 cases in total and saw 3 cases with 1-minute updates, 3 cases with 2-minute updates, and 3 cases with 5-minute updates. All data they saw were collected by the SPY-1A phased array radar in Norman, so it was all single polarization data, which allowed forecasters to look at reflectivity, velocity, and spectrum width. In each case, they would issue severe thunderstorm and tornado warnings, just like they would if they were in their local office working the event. While they did this, there were several researchers in the room, and we just listened and watched them work, which by itself was really interesting. They would always share these little stories in the breaks or say something like, "Wow, I wish I had that kind of data in my office." But we went a lot further than simply listening and observing. Immediately after the case ended, they watched a video of their screen activity and typed out everything they were seeing, thinking, and doing during each 5-minute period of the case. This activity gave us a lot of insight into their warning decision process. And then we also held focus groups to gather even more feedback, thoughts, and insights into what they thought about the different radar update times and how the data could be best used. We also took it one step further and ran one case with eye tracking software. Basically, we took forecasters into a dark-ish room, like what you see in the picture on the right, where they worked a case issuing warnings. Specialized equipment tracked the location of their eyes, where they were looking on the screen over time, which gave us information about what they were looking at, when they were looking at it, and if radar update time may have affected how they interacted with the data. So we collected a lot of quantitative and qualitative data to figure out if radar update time matters. After the experiment was done, the data analysis began. Through the analysis, we saw several common themes emerge that were also consistent with results from the other Paris experiments. For example, tornado warning lead time was longer, probability of detection was higher, and false alarm rate was lower when 1-minute update data were used, and that can be seen in the table. It was also interesting to find that forecasters using 1-minute data issued noticeably better warnings than those using 2-minute data, which highlights the benefits of the rapid scan data a phased array radar can provide. This improved performance likely occurred, at least in part, because forecasters frequently mentioned having higher confidence in the warnings they issued when using 1-minute data, because the data looked more like the conceptual models they had in their head. Basically, the data looked more like the real world without those longer gaps that occur in between the 5-minute data when that was used. We also compared warning characteristics such as size and duration for each radar update speed. And we found that the warnings basically looked the same regardless of the update time. So radar update time appears to affect when the warnings were issued, but not how they were issued. In other words, the warnings were issued earlier, as evidenced by the longer lead time. But if you looked at all the warnings issued with 1-minute and 5-minute data, they basically look the same. Therefore, it's probable that to fully realize the benefits of rapid update radar data, some changes are needed regarding how radar data are displayed, as well as training, and then also adjustments to the warning paradigm itself. And these were ideas that were frequently brought up during the focus groups. As I mentioned earlier, all of these results are for single polarization data. But what about dual pol data? How might that be beneficial to forecasters? Well, while the ATD was being developed and made ready for operations, we used a research WSR-88D in Norman called KOUN to collect rapid update data that would likely look similar to what a dual pol phased array radar might collect. We collected a 90-degree sector and used customized scanning strategies to get update times of about 1.5 to 2 minutes. Over the past 5 years alone, we've collected about 70 cases as a first step in figuring out how rapid update dual pol data might be beneficial to forecasters. From that data set, we have done several studies to examine if dual pol data can be used to help forecasters gauge storm severity. And as it turns out, dual pol data can help. We have seen promise with dual pol signatures related to hail and downbursts. To show one example, we looked at a dual pol signature related to the strength of a storm's updraft, called a ZDR column. We found that stronger ZDR columns are more likely to be associated with severe thunderstorms. In addition, ZDR columns tend to develop and intensify earlier than upper level reflectivity cores, which forecasters typically use to issue severe thunderstorm warnings. Therefore, ZDR columns could help forecasters know that a storm is severe and know that it's severe sooner. Now, rapid update data is especially important here, as the animation on the left does a good job of showing that rapid update data provides a more complete picture of how this important signature evolves over time than, say, the traditional update data at 5 minutes would do. This matters because we found that rapid update data captures relative maximums in ZDR column strength earlier and more often than traditional update data, as seen in the box and whisker plot. There was more lead time, if you will, between when the ZDR column reached a relative max and when severe hail was reported for the rapid update data relative to the traditional update data. and the rapid update data captured these relative maximums in a higher percentage of storms than the traditional update data did. Essentially, the rapid update data was less likely to miss these relative maximums because they were less likely to fall in between successive observations. We have also used KOUN to collect data for flash flood events to see if radar update time would impact the accuracy of hydrological models. In one study of a flash flood event in the Oklahoma City area, we looked at various data sets with different update times and spatial resolutions. Of all the observational data sets, the hydrological model that used rapid scan KOUN data performed the best. When compared with 5-minute data from a nearby operational radar, we actually saw that the model using 5-minute data missed about 50% of the flash flood area, as seen by the lack of warmer colors in the left image, especially in the northwest part of that stream basin. Therefore, the most accurate projections of flash flooding might be achieved using rapid update dual pol data. So where do we go from here? We plan to continue looking at how rapid update dual pol data can help forecasters anticipate things like downbursts and tornadoes associated with squall lines. We will also extensively use the ATD to figure out the best scanning strategies for each type of severe weather in terms of update time, spatial resolution, and data quality, and determine how each one of those factors might impact how forecasters and algorithms use radar data. We will also work with engineers to develop advanced scanning strategies that help us know the best design for an operational network of phased array radars that's going to ultimately provide forecasters with the radar system they need to most effectively protect lives and property. This idea also applies to existing and future radar algorithms that can assist forecasters. So we will look at how algorithms can best take advantage of the faster and more adaptive capabilities of a radar like the ATD. Last but not least, we will evaluate how rapid update dual pol data can best be integrated into the National Weather Service of the future that appears likely to take advantage of high-resolution computer forecast models in a war on forecast system that can benefit from assimilating rapid update radar data, as well as rapidly updating probabilistic warnings and MRMS. No doubt, there is a lot of exciting multidisciplinary work ahead. Next up, Kurt Hondl will be talking about future plans for NSSL with respect to phased array radars.
Hello again. My name is Kurt Hondl. I'm the NSSL Deputy Director and Phased Array Radar R&D Program Manager. You just heard about some of the exciting research that we're doing here at NSSL on dual polarization phased array radar. I'd like to point you to this recent article that summarizes some of our current understanding of the technical capabilities of phased array radar, some of the remaining challenges and risks for phased array radar technology, how the data can be used to benefit NOAA's mission to provide warnings and forecasts, and also some additional concepts about how we get to the radar of the future. 2 years ago, Congress asked NOAA, what is your plan for your future radar and the replacement of the 88D? And so NSSL, along with OAR headquarters and National Weather Service headquarters, collaborated to write this weather radar follow-on transition to operations plan report that was sent to Congress last year. It has 4 key elements. The first is to sustain and enhance the NETRAD network through its current expected service life, to continue the phased array radar R&D to reduce technical risk so that we can be in an informed state when it comes time to make a decision on a future acquisition. Also to protect the NETRAD spectrum from encroachment from other users and interference from things like wind turbines and wind farms. And finally, to organize for success. That means that OAR and National Weather Service headquarters, along with NSSL, working together to plan our future R&D and strategize for the acquisition of a future radar. So this timeline is a tentative timeline that was provided in the Weather Radar Follow-on Plan report. If you look at the green line there, that is our acquisition timeline. And starting from the right-hand side and working back to the left, the plan is to have a new network of radars completely installed by 2040. That means that we would have to start deploying radars no later than 2035, and that would mean that we would have to have a contract in place by no later than 2032. In order to meet that goal, NOAA would have to publish a request for proposals around the time frame of 2030. And what that means is when you publish the RFP or the request for proposals, we're defining what the future requirements of NOAA's weather radar will be. And in order to do that, by 2028 or 2029, NOAA will have to complete an analysis of alternatives that looks at the cost benefit of the different alternatives. And there are three primary alternatives that we've identified. The first alternative would be to perform another service life extension program for the NETRAD system. This might be an option if phased array radar needed more time for development. Alternative two would be to replace the NETRAD system with a modern reflector dish technology. This may be the preferred alternative if for some reason phased array radar is either considered too expensive or otherwise not a viable replacement candidate. Alternative three would be to purchase and deploy phased array radar technology. And this alternative, there might be multiple phased array radar configurations that we would want to analyze based on the trade-offs between different technologies, capabilities, and cost. So this timeline gives us about 8 more years for phased array radar R&D to drive down the technical risks and make sure that the phased array radar is a viable alternative as a NETRAD replacement. That includes additional technology demonstrators and industry engagement so that they can better understand our requirements and unique needs. So what will the phased array radar alternative look like in this scenario? I can't answer that right now. You'll have to come back in 5 years at the next NSSL science review, and we'll be able to give you a better idea of what that will look like. So we've got a lot of work to do in the next 8 years. The first thing we have to do is obtain all the information that we can from the advanced technology demonstrator and what we learn about the calibration of dual pole phased array systems, what we learn from our meteorological R&D and on rapid update dual polarization data. We also have several other engineering demonstrators and research activities funded at some partnering institutions, most notably the Advanced Radar Research Center here in Norman, Oklahoma, and at the MIT Lincoln Laboratory up in Boston. And finally, we have to continue the research that we outlined in the Weather Radar Follow-on Plan to reduce the technical risk of phased array radar technology and to work with Weather Service and OAR headquarters to establish collaborative plans for our continued R&D and the acquisition planning for the future radar. So looking ahead to our next science review. I'd like to be able to talk to you about our alternative for a phased array radar technology as a potential replacement for the NETRAD system, and looking forward to how we can ensure that phased array radar technology can not only meet the current Weather Service requirements for radar data, but is able to meet the future weather radar requirements for the forecast office of the future. And we'll be interested to see what that phased array radar alternative looks like. So if you go to this website on the link here, you'll be able to see more pictures and video of the advanced technology demonstrator. On behalf of NSSL and the Phased Array Radar R&D team, I thank you for your time, and I look forward to discussing this program with you during our NSSL science review. Thank you very much.